Thank you, Patrick. Hello, everyone, and thank you so much to Patrick and Lou for inviting me to speak to you today about our work at Cortical Labs. It's a long journey, but I think this is a great city and a great venue and great people to talk to. So we've heard a lot about AI today, and I don't know about you, but there might be a little bit of inferiority complex coming in from being a biological system. We hear about AGI and ASI, and we wonder, is there any role left for us, right, if these machines are so superior? I'm just going to walk you through. There are some things that we are still good at, and namely, we're going to talk about biological computing with these neurons and how we can leverage the strengths of biological systems to complement the silicon that we see today. So there is a well-known paradox known as Moravec's paradox in the space of robotics. Essentially, what Hans Moravec posited is that he observed that skills that we take for granted, that are very easy for us to do, physical skills, such as making a cup of coffee, riding a bicycle, extraordinarily hard for machines to do. Conversely, the skills that we find very difficult, say abstract reasoning, large computational processes, what machines excel at. And you can actually see that things such as language, reasoning, thinking, are all relatively late-stage evolutionary traits that only we think a handful of species possess, namely us, Homo sapiens, the primates, and other species. But the ability to control our embodiments and operate in the real world has actually been very well preserved and evolved over millions of years. And if you think about this, the ability to be embodied in the real world, to operate in real time, was probably associated even with the dinosaur period. So having said that, I'm going to segue into the question of computing. And really, it's a story of two things. It's a story of bytes and a story of watts. Let's start with bytes. So this here is a table indicating the amount of data that was used to train various systems. The one that I want to draw your attention to is Common Crawl. Common Crawl is essentially the entirety of the open internet up to the point of, I think, 2021 or 2022. And so at that point in time, the internet contained 410 billion tokens. And it wasn't until we ingested this amount of data and the evolution of the transformer model that led to the large language models that really saw the explosion in interest in artificial intelligence that was really the catalyst for it. The issue with this, however, is that we're running out of it. In fact, we might have actually run out of pure human-generated data. And last year, Ilya Sutskever, who's the former chief scientific officer at OpenAI, in his acceptance speech for the Test of Time Award, actually likened data to a fossil fuel. We accumulate it over the years. It sits in our repository, and once we've used it, that's it. We're not producing any more pure data. And so this is, I think, a very pressing matter, particularly in the AI industry, as we know that if you actually feed outputs of the AIs back into themselves using synthetic training and so forth, you somewhat amplify the errors and hallucinations, and you end up with a phenomenon known as model collapse. So this is a thing that we have to be wary about. The second one is, and we've heard a lot about this, is the question of energy. So this is a chart of how much energy that was used to train, I think, GPT-3. And as we now know, there is talk about gigawatts per week to train even larger models. And we hear about the need to spin up nuclear reactors and so on and so forth. This has many downstream effects, particularly to us, average people. The energy that we use comes from a common market. So if there's more demand for energy, the prices go up. So this is not good, particularly for when there is a cost of living crisis or when there's inflation. So we do need to think about how are we going to solve these things without bankrupting ourselves in terms of energy. So let's talk about robotics and how we're trying to approach this in silico, which is, I think, the next big breakthrough if we can get there. So this is a video of a simulation in the NVIDIA Isaac software package. And what you can see here are lots of simulated hands manipulating a cube. This is only possible in silico. And that's because in silico, you can replicate lots of models. And this is a slowed down version. But in most cases, simulations are run at 100, 200, maybe 500 times faster than real time. That is done to accelerate the amount of data that is captured and collected. But one thing that biology has actually excelled in that solves for these two problems is that we have to obey the laws of physics, i.e., we cannot consume more energy than what we can hunt or forage, or eat in this case. And we know what happens when you do that. You die. You cannot speed up time. And you can't create more physical instances of yourself, unlike in a simulation. So with these constraints, evolution has really honed biology to be very good at using whatever data, whatever energy is at hand. So let's take, for instance, one of the model organisms for this. This is a dragonfly. It is nature's most effective predator. It has about a 95% kill rate, and only has about 1 million neurons and consumes about 0.5 milliwatts of energy to 200 milliwatts of energy, depending on whether it's at rest or it's in flight mode. But let's watch what happens here in this video. Yep. Let's go back. If we can play the video.
It's off screen right now, but it's locked in. See it take off, accelerate, there's the target. Approach, and wait a minute, that's not a meal. That's like a pine needle or something falling out of a tree. Although this dragonfly nopes out of the chase when it realizes its mistake, we still get to see how much thought the dragonfly actually puts into its pursuit. You may think that it sees a target and flies straight at that target until it catches something, but it doesn't. It actually predicts the path the target is taking, chooses an interception location and an interception time, and then gets there to make the catch. Or, in this case, not quite. Since the target here is just falling at a nearly constant speed, the dragonfly makes a really good initial guess at the interception location, and it flies on what's basically a dead straight line to that interception point.
So this is a really interesting example of biology being very good at control systems. This is running with a camera that's at 100 frames per second. So this is 1/10 a second of what you're seeing in terms of the accelerated time. So it's had to do this compute at that short period of time with that little amount of energy, and yet it's so accurate at predicting where the trajectory of the prey, in this case, or the not prey, was going to be. So biology has, I guess, perfected that form of control. Now, we're very good at reasoning, but we're not the only species that can also reason. Let's have a look at one type of reasoning. And we can play the video.
Was the block push. Once again, she got to this point and was sort of stumped without an obvious path forward. But this is where their natural curiosity pays off. Because she's not just feeling surfaces with her arms, but also constantly pulling and pushing to see what she can interact with. And so sort of by default, she figured out this red part of the wall doesn't push back as hard, which cleared the way up to the ball drop. And I knew this one would be tough for her because number one, there's not enough room for her to just squeeze by. And number two, pushing and pulling on walls wasn't gonna solve it either. And after struggling in vain to find out what she was supposed to do for quite some time, eventually she got frustrated and just stopped and sat there. Almost like she was processing all the data she just gathered. And this was the moment I knew for sure I was in over my head. Because while basically maintaining eye contact with me as a flex, she reaches up with one arm and then twists the bar which dislodges the ball, allowing her to clear them out and move on. And this feels like the perfect moment to tell you that my absolute favorite fact about the octopus is that they are truly the closest thing we have to intelligent alien life on this planet.
So I guess you won't be eating octopus with the same feeling after seeing this video. I certainly didn't. So what we saw there were two organisms that had control systems and intelligence that have evolved biologically, and most of them are controlled by neurons. This addresses two bottlenecks, I think. Firstly, there is the architectural problem, and as we previously heard about von Neumann architectures, this is essentially a big problem. I'm going to show you the pointer here. The bus that we use to transport bytes from compute to memory and back again is very inefficient, and in fact uses about 90% of energy and converts it mostly to heat. Right now, one of the challenges of actually scaling silicon is actually heat dissipation. So one thing that's really interesting is that biology actually doesn't do that. As far as we know, there is no separate part of a neuron that deals with memory and compute. It is actually part of the same package. So I think this is a very interesting question. Can we build systems that eliminates this bridge altogether? Quantum might be one, biology may be one, neuromorphic might also be one. The second one to think about as well is this question of the algorithm. So everything that we've seen in the AI space can be traced back to this one algorithm, and that's backpropagation, which is how we flow the error signals that we get as we do a forward pass training to improve on the neural networks. So this is what's powering convolutional neural networks for image recognition, transformers for large language models, and even the diffusion models. One of the problems of this algorithm, however, is it only allows you to solve for problems where your objective or your loss function is differentiable. And there are a lot of problems out there in the world that are non-differentiable. So I think we need to start thinking about what is next beyond backpropagation. There is some thinking that perhaps it's happening in the brain, but it's very hard to actually figure out how that's happening, given that we've only been able to model and to see neurons doing forward propagation. So let's go back to the brain. It's really interesting because it does all the things that we marvel that our computer is doing recently. It can reason, can talk, can autonomously be embodied in an environment. And it only takes about 3 to 4 years of real-time training before they start talking. And if anyone has 2 or 3-year-olds, you know they won't stop talking. And it also only consumes 20 watts of energy. And that's every one of us here carrying that in our heads. So what do we do then? At Cortical Labs, we thought, wouldn't it be interesting if we could use the same building blocks for the brain, that being the neuron, to do compute, right? Because if brains can do intelligence, and it's probably the only thing that we know is generally intelligent, and if a brain is, in most cases, thought of as a computer, then wouldn't the neurons be considered the transistors for that kind of computer? So we published our work in the journal Neuron in 2022, where we actually prove that you can take neurons grown outside of a body, put them on a chip, and train them to do a task. In this case, was playing the classic Atari game Pong. So what does it look like? So this is a scanning electron microscopy image. 10 microns is the width, 1/5 the width of a human hair. And you can see this is an axon running across, and these are all the dendrites making synapse connections. But you can see a bit of a groove here, and this is actually the groove of a CMOS chip that we were growing our initial neurons on. And here's with some false coloring. You can see the silicon, the neurons. And as we zoom out, you can see a much greater complexity in that structure. What it actually looks like is this. This was a chip that we used that had a CMOS CCD that we were able to grow the neurons on. And because neurons communicate electrically between one another, we're able to pick up that signal on this CCD and also provide a stimulus back. So in some cases, we were eavesdropping and also whispering back to the neurons what we wanted them to hear or do, and what they were also saying. So moving on from that, how do we get these neurons, you may ask? Well, at my lab, what we do is we grow these neurons from induced pluripotent stem cells. So about 10 to 15 years ago, a breakthrough was made in Japan by Professor Yamakana and his colleagues that showed that if you apply 4 compounds, you can actually reverse the age of any adult cell back to its embryonic state and become a stem cell. And so that's what we do. We take blood, sometimes skin, and we transform them back to become stem cells. And from stem cells, they can become anything, and we specialize at growing neurons. So we grow those neurons from the stem cells and plate them on these circuits. What then happens is, I'm going to show very quickly a video of what happens in our lab, and this is me for Cameo. They sit in a well that contains cell culture, tissue culture media that keeps the cells alive, gives them the nutrients that they need and the electrolytes and growth factors. And this is a different type of chip. This is a glass chip with titanium nitride electrodes, where we can now also do microscopy and actually see what the morphology of these neural networks are doing, while at the same time doing the electrophysiology, thereby giving us both the morphology, which acts as a bit of a ground truth because we can see that, and also the electrical activity. I'm going to skip this to the next slide. And what we did was we put a lot of different disciplines together into a pot and stirred it all together, and we ended up with the results of our experiment. But it did take quite a bit of convergence. We needed stem cell tissue culture people. We needed neuroscientists. We also need theoreticians in the form of the free energy principle, which is a theory that was developed by Carl Friston at UCL that tries to explain intelligence. And we also needed quite a bit of software engineering to build a closed-loop system, in this case, the game of Pong. So how does it work? We take a chip, we put the neurons on it. Some neurons are the sensory region, some of them are motor regions. And then I'm going to click here to see, if I click here to see if I can play the video in the Pong game, can somebody click? Oop. Yeah, there we go. This is a recording from our system where that paddle there is purely being controlled by those neurons. There's no machine learning, there is no programming, and all we did was we said, here's the relative position of the ball to the paddle in the x and y axis, and you motor regions that are designated the up. If you have more activity up, we'll move the paddle up, and if you have more activity in the down, we'll move the paddle down. And on top of that, we also gave it a incentive and a disincentive, sometimes in reinforcement learning known as the reward and the punishment signal, where every time it hit the ball, it was rewarded, and every time it missed the ball, it was punished. And if you do this over and over again, they actually start learning to play. So what does it look like? We're just going to go to the next slide, and we're going to see a live stream, which we'll switch to on a laptop connected now. So here's a live stream of neural activity coming from our lab all the way in Melbourne, Australia. It's pretty hard to bring the cells along, so this is as close as it gets. But what you can see here, there's no machine learning, there's no compute going on. These are actually being generated by the neurons. But you'll see some very interesting characteristics. You get spike trains, you have a burst of activity here, and more spike trains, and then they start to coordinate. And they have very interesting properties, very similar to what you'll see in living biological systems. And we can also show the activity right here in a spatial pattern. We can see more activity and more details with our waveform viewer. So you can see every time there's a spiking activity, we mark it with a blue line. And every time that happens, we also flash the electrode. And that's what you're seeing here. But there's a great deal amount of granularity that you can now get using this kind of system. And if we switch to the next tab, you'll see actually one of the systems is actually running the Pong experiment, and it's controlling that paddle in order to try to play and intercept the game. which is quite phenomenal, so to speak. All right, is it going to hit it? Yep, there it hit it. All right, so we'll move on to the next slide. From here, oop. So how does it work? Let's go next. Very quickly, because there's a lot of theory involved with this, the free energy principle posits that the brain or any biological system is a Bayesian generative machine. What that means is that we have beliefs of what the world is, and we have the ability to prove or disprove our hypotheses and beliefs of the world through our senses. But we don't not just have senses, but we have motor functions, and we can do mini experiments, such as picking up the bottle of water and dropping it and seeing the effects of gravity, and so on and so forth. And this is separated between what the real world is, which has its own distributions, and our internal beliefs by a structure known as a Markov blanket. We assumed that there was also the same structure in the biological system. The neurons have its own internal distribution and beliefs of what the world is. The Pong game provides an external distribution with structured information, rewards, punishments, and so forth. And what we do over time is that we try to get these neurons to get very good at predicting that external world. And it turns out that all we need to do in order for this to work is to reward them with a sine wave and punish them with white noise. And you may ask, why is this the case? Well, the reason why this is the case is that sine waves have very low information entropy. From one period, you can extend it all the way out to n number of periods, but you can't do the same with white noise. You cannot extrapolate white noise. And it turns out if you do that, you can modulate the overall information entropy of the system. And what's really interesting is that this system does not do any backpropagation. It's online learning, which is more applicable to us because we're continuously evolving our intelligence. Like right now, your intelligence is different than what it was 5 minutes ago and will be 5 minutes in the future. We don't have the same things with our artificial neural networks. Once you've trained your system and you've frozen the weights and you go into inference mode, those weights don't change. And what this actually means is that we have fluid, not crystallized intelligence. And I think this is really interesting. And here's some data from the paper. You can look at it later. But I'm going to skip really quickly to this one here. Everyone can see this, and the first thing you know is to run. Or maybe if you want to fight it, you can as well. But what's really interesting is that our visual system and our cognition is so fast that machines require several hundred images for this to sink in and for it to learn. Fortunately, tigers don't really eat robots or computers, so I think they have that time. But for us, we've evolved to be really quick at recognizing this. And so this became the subject of a follow-up paper. We said, try to answer the elephant in the room, why bother with any of this? And we said, why don't we try comparing this against a model-free system in reinforcement learning versus the biological system? So we did exactly that. We gave it the same game between what we trained the Pong system and a reinforcement learning agent. But what we did was we sample constrained it and said, you're only going to get 20 real-time minutes of gameplay. And what we did was we benchmarked it. And it turned out that with even more information than what's given to the biological systems, the biological systems outperform reinforcement learning agents when the time is constrained. Now, this is really important because robotics is a space where time really matters. And if we decimate that, you will see an even greater delta. Very quickly, I'm going to rush through a couple more slides, but what's really interesting is also this paper that came out. So this is not just a platform for compute, right? Because we're actually growing these neurons from stem cells, they are essentially real twins. They're not digital twins, they're real twins that inherit the same mutations, so therefore disease states, drug resistance, and so forth from their donors. And what that allows us to do is really interesting work in personalized medicine and drug discovery. So very quickly, I'm just going to go through this. What we did was we grew cells that looked like they had epileptic seizures. We recorded their activity, and then we put them through the gameplay. Now, all of them responded to anti-epileptic medication, And that was good because when they had seizures, they couldn't learn to play. However, this showed a very more interesting nuance, that when you put them into the gameplay state, only one drug with that dosage had any real statistical significance in the gameplay performance. Now, why does this matter? Because now we potentially have a window to looking at what the cognitive effects are and the cognitive state of neurons in an in vitro setting. And I think this is going to be a potential game changer. So here's a CR1, very quickly, made in SolidWorks. Thank you, Dassault Systèmes. The next phase for us was to try to figure out, well, now that we have all of this, how do we bring this to the market? How do we get our academic colleagues to come on board? And so this is a CR1 system that we have built. We'll be around tomorrow, so please come by and talk to me if you want to find out more. And it forms a new paradigm of thinking of what a biological computing system is, because you have hardware, software, and now a second dynamic lever, which is the wetware component. And this is Andrew, who's our chief hardware engineer, loading a CL1 into a server rack cabinet. And then very quickly, we're going to skip through this. But here's where we're thinking in the next generation. How do we make chiplet modules? How do we increase the performance of these systems so they're not growing wild, but they're actually being directed so that we get more compute? And by doing this, our next set of experiments is, can we get MNIST, which is the image recognition challenge, to work with these neurons? And by having this structure, we're actually getting about 80% accuracy now. We're building software so that you can actually start programming these systems using high-level languages such as Python. And just very quickly to summarize, we're just at the start of this, right? Silicon has had 70 years to develop. We've only just been around for 6 years, and we're only just getting started. But I think this is a really great and exciting space. And with that, thank you very much for listening to my talk.
Hey, here. Wow. Wow. And it's not because you're using SolidWorks. Wow.
Yeah.
This is mind-blowing. We have time for questions. I know we're out of time, but I don't care. I have so many questions for you.
Yes.
First question. Do you consider yourself to be a high-tech company, a biotech company, a high biotech company? What are you?
Well, that is a good question. And this is one of the problems with what we're doing, because we don't really fit into any bucket.
Exactly.
And I guess this is the reason why the term deep tech exists, right? It's a catch-all term for something that doesn't quite exist, and you just need to categorize it somehow, so it just falls into the other bucket, which is deep tech. So I think that's what we would be considered as. But in many cases, we're really a science company that is now starting to try to get more people to build and experiment with the system. Just like the early fathers of silicon, right? Yeah. We didn't know that silicon could be used not just to do calculations, right? Because that was what they were initially used for. But by building abstractions of calculations, you could build applications that could get you a taxi, find you love, listen to music, watch videos, and so on and so forth. So I think there are a lot of applications that we haven't thought about yet, and that's because we haven't gotten the technology into the hands of researchers and developers out there.
Wow. And I have a last question from my side. Since you're relying on real neurons, there is this plasticity. Do you think your infrastructure can also provide new ideas for the new architectures for AI to be more fluid, more dynamic, and continuous learning? Because some are trying to do so, but not totally inspired by nature.
Yeah, absolutely. I think this is a great use case for trying to see if there is a ground truth, poking, prodding, understanding what these things are doing, to flow it back into more informed approaches to building, I think, novel silicon. One actual, not really about AI, but the other flip side of what we're doing is actually brain-computer interfaces. And some of my team just dropped off a unit at Dartmouth who are actually planning to do more work in brain-computer interfaces, but want to also use this kind of system to understand, well, what is actually happening? How do we read signals better? How do we write information back into these biological systems and ultimately into the brain? So I think, definitely will help AI systems improve. But on top of that, I think brain-computer interfaces is extraordinarily exciting as a space, and whatever else that comes from there.
Well, is there any last short question here? Many, actually. We're out of time, but that's my fault. So let's go to them.
Well, thank you very much. That was a very exciting talk. I just have one question. How did you come to know that the sine wave did the trick while training them?
As they say, necessity is the mother of all inventions, and being poor makes you think harder. So initially when we set up the lab, we bought all these electrophysiology equipment, and by the time we did everything, we realized, damn, we don't have enough money to pay, sorry, we didn't have enough money to do dopaminergic excitation. So we were stuck with all this electrophysiology equipment, and we had to think harder and say, well, there's this theory developed by Carl at UCL. What if it's true? And if it's true, then changing the entropy should work, right? So we then started to think about it, and then we said, wait, a sine wave has like very low entropy, and white noise has like extraordinarily high entropy. So we just tried it, and it worked. So in many cases, I think having that constrained resource pushes you to think creatively about how you can try and solve the problem. And in this case, we just tried it because that was the only pathway we had.
Thank you very much. One last, because we're really out of time, so one last.
Thank you very much for the very interesting talk. Now, I was wondering, with this theme of using a game such as Pong for these benchmarks, what could be the next environment or game for benchmarking this technology looking into the future?
Yeah, so when we announced this and the paper came out on the internet, I think the first thing that everyone said was Doom, when? And like everybody wants to put Doom on every damn machine, right? So it's been on our roadmap. However, even with a Pong game, we're not really playing Pong. Because when you play Pong, you're actually looking at the pixels, and you're playing it based on vision as the input. What we're doing here is a mixed rate and place coding. So it's very similar to how the whiskers of a cat or a mouse works. So imagine if you had whiskers and you could tell where the things are. That's how we're feeding the information in. Doom, you can't do that. It's a lot more complex. So the reason why we've been doing vision as the next extension to our work with the Pong is so that we can actually have the first foundations to get Doom to work, which is feeding pixels in, getting the neurons to understand what is happening, and having to respond back. So I think it's a natural progression with 2D games, more complex 3D, and eventually, we can have realistic simulations and so forth. But I think control systems-wise, if we have very simple experiments, and Pong is a good example of just a control systems process, going actually back to simpler things such as maybe a cart pull or a reverse pendulum problem will actually help us understand at a much more fundamental level how to manipulate these systems to get them to do what we want them to do. So bit of a yes and no answer, but yes, we want to do Doom, but we also need to understand more fundamental what's going on with these systems.
Fascinating. Let's thank again Hon for this incredible presentation and adventure. Thank you so much.